In this video, you're going to learn how to interpret a seismic shot record. When you look at a seismic shot record, you will see different seismic trends, and in order to process the data, the first step is to identify those trends. And this is something that you're going to learn in this lecture. Let's get it started. Here you see a seismic shot record for a data acquisition where the source was located in the middle of the array. And something that is noticeable in the beginning, you see some linear events, and the reason why I'm saying that a linear event, because if you look at them closely, if you consider this axis to be distance, and this axis to be time, the relationship between distance and time is linear. Then you may notice some hyperbolic events. And also you may see some, again, linear events by dispersive nature. So in this video, we're going to delve into each of these events to get better idea about what they are and how to interpret. In the beginning, I should clarify some important terminologies. So one of them is offset. That is the distance between source and receiver. For example, when we say that the offset is 100 meters, it means that the distance between the source, for example, dynamite, and the receiver or geophone, or maybe in your land seismic data acquisition, is linear. Another important terminology is travel time. Travel time is the time for seismic wave to get to recording station from the source. Now, just let's talk about wavefront. This is another important concept. Once we activate the seismic source, the seismic energy propagates through the earth in the form of a sphere or spherically. So we have a pocket of the energy that propagates like a sphere. And when the seismic waves travel further, this sphere becomes bigger and bigger. And this sphere is called wavefront, and indeed wavefront is a surface that connects all the points with the same phase from the source. Just let me give you this video, and this is a YouTube video, and this is a very insightful it is very insightful in order to get some idea about the concept of wavefront. The source is located at this point, and the source is activated, and you see the wavefront in the beginning. And this is for a numerical simulation, and a synthetic geological model has been simulated in computer. And this is a famous model called Marmuzi model. It is very complex scenario. Once we activate the source, the seismic wave propagates within the earth. In the beginning, it is spherical, but once the wavefront impedes different geological layers, its geometry becomes more complex. And the further that the wavefront propagates, it becomes more complex in terms of geometry. At the same time, you may notice that once the wavefront impedes different layers, a fraction of the energy is bounced back to the surface. So if we have some geophones, we are able to record them. Now just consider a pair of source and receiver. Definitely, if you want to just think about the wavefront and how the source receives seismic signal in terms of wavefront, it is very complex procedure in terms of imagination. So you have to have a strong imagination in order to have some idea about the pathway of the source, and that's the reason geophysicists use another terminology or concept that is ray path. So ray path is a vector that is perpendicular to to the wavefront, and indeed it is much easier sometimes to show the travel route for a seismic wave in terms of ray path. And this is something that I'm going to follow in this lecture for the sake of simplicity. But notice that what is really happening in the real world is the propagation of a complex wavefront. The first wave type that we see on a seismic shot record is direct waves. Direct waves are those waves that travel directly from the source to the receiver, and the travel time of seismic wave is given by this equation. T sub d is equal to x over v1, and v1 is the velocity of the medium. So when we look at a seismic shot record, the first group of waves that we see can be interpreted as direct waves, and they usually appear as first arrivals at near offsets. Another group of seismic wave that we see on a seismic shot record is refracted wave. And in order to explain the concept of refracted wave, just let's review the concept of Snell law first. So Snell law predicts the incident and transmitted angle for a seismic wave in the boundary of two geological layers. So assume that we have two different geological layers with different seismic velocity. The velocity of the first layer is v1 and the velocity of the second layer is v2. And here is the incident angle for the P wave. So once the P wave impedes the boundary, a fraction of the energy is reflected back to the surface, and you see if we consider a line that is perpendicular to the surface, the angle between the incident wave and that line is theta 1, so the reflected angle also will be theta 1. But the transmitted angle will be theta 2, and that can be different from theta 1. And indeed, when we have velocity contrast, it is different. And Snell law says that this is a relationship between V1 and V2, and based on this relationship, we are able to predict the value of theta 2 based on theta 1, V1, and V2. Consider a geological model where V2 is greater than V1. According to Snell law, we know that sine theta 2 is equal to V2 over V1 times sine theta 1. And because V2 is greater than V1, V2 over V1 is greater than 1. So we may conclude that sine theta 2 should be greater than sine theta 1, and as a result, theta 2 is greater than theta 1. So this is very interesting. So in other words, once we increase the incident angle, at the same time, the transmitted angle becomes larger and larger, and at a specific angle that is called critical angle, the transmitted angle becomes right angle perfectly, and that angle is called critical angle. And the wave, in such a scenario, the transmitted wave travels in the boundary between the two layers. Now just let me explain it here in this image better. So once we, for example, hit the plate by a sledgehammer, the seismic wave travels, and you see this is how refracted wave travels indeed. So the refracted wave travels in the boundary between the two layers, and once it's traveling at the same time, it radiates a fraction of the seismic energy to the surface with the same incident angle. And this is how we are able to record refracted waves. So in other words, just if I wanted to make it clearly, so This is how the refracted wave travels. And at the same time that it travels, it radiates a fraction of the energy to the surface. Just let me show you this interesting YouTube video. So you see that the source is activated. You see the direction or the travel path of both direct and refracted waves. At near offsets, direct waves get to geophones first, and after a specific distance, these are refracted waves that get to geophones first. And the reason why at farther offsets, refracted waves get to recording stations or geophones first is that they travel with the velocity of v2 in the boundary between two layers. And as a result, they travel faster, but their travel route is longer. So that's the thing at near offsets, direct waves get to geophones first because their travel path is shorter. But at farther offset, these are refracted waves that get to geophones first because although they are passing a longer route, but they pass that route with higher speed or velocity. Now consider a geological model where the velocity of the first layer is 1500 meter per second and the second layer 3000 meter per second. Calculate the critical angle. So for this example, the critical angle is 30 degrees. This figure shows the travel route of refracted waves, and you see the travel route is trapezoidal, and this equation is the travel time for refracted waves. So again, if you look at it closely, you may notice that the again relationship between t and x is linear. When you look at seismic shot record, as I said, at farther offset, the waves that get to geophones first are refracted waves. And you may ask me the question how we can identify or how we can distinguish direct from refracted waves. So it is easy. If you zoom in on your shot record, usually direct waves have sharper slope compared to refracted waves. They are more gentle. And this is how you're able to identify them. So just do some zoom in and zoom out and just look at the direct wave trend. Once the direct wave trend changes, you may say that, okay, after that, you have direct wave. Another important concept in reflection seismology is the concept of acoustic impedance. Acoustic impedance is the product of density and velocity, and it is indicated by Z. Z is equal to rho times B. It is very important geophysical parameter, and in particular in quantitative interpretation, we can obtain many petrophysical properties of subsurface such as porosity from acoustic impedance of subsurface layers. So assume that we have a seismic wave with the incident angle of 0, so it impedes the surface vertically, and as a result a fraction of the energy is reflected back to the surface and a fraction of the energy is transmitted to the second layer. Now you may ask the question, what fraction of the energy is bounced back to the surface and what fraction of the energy is transmitted to the second layer? We can calculate such a thing using reflection coefficient that is given by this equation. So in other words, if we have if we have A, that is the initial amplitude of incident wave, the amplitude of reflected wave is equal to A times R. R is the reflection coefficient. So this is how we are able to calculate the amplitude of reflected waves. Similarly, the amplitude of the transmitted wave is given by A times transmitted coefficient, and something that is noticeable here is that R plus T is equal to 1. Now assume that we have such a geological model. Calculate the reflection coefficient. For this geological model, the reflection coefficient is 0.35. Similarly, you can easily say that because reflection coefficient is 0.35, the transmitted coefficient should be 0.65. Now just let me ask you another question, and this is more insightful. Consider another geological model, and here is for a scenario when the reflection coefficient is negative. So if you calculate, you see that the reflection coefficient is minus 0.53. Similarly, the transmission coefficient is, yes, 1.53. Just let me ask you this question. What is the meaning of negative reflection coefficient? Negative reflection coefficient means that the polarity is reversed. So if the polarity of the incident wave was like positive, it becomes negative and vice versa. So what is the physical concept behind transmission coefficient greater than 1? It is so interesting too. It tells us that if we have such a geological condition where Z1 is greater than Z2, the transmitted wave will have a larger amplitude compared to the incident wave. So in other words, the seismic amplitude increases for transmitted wave. Consider this geological model. When should we expect to have reflected seismic data in the boundary between two layers? Yes, we should have some reflected waves if there is a contrast in the acoustic impedances of two layers. So if the two layers have the same acoustic impedances, then we're not going to have any reflection. This figure shows the travel route of reflected waves, and this equation is the travel time for reflected waves. And if you look at it closely, you will notice that the relationship between x and t is not linear anymore, and it is hyperbolic. And indeed, reflected waves can be identified on a seismic record as hyperbolic events, and the reason why they're hyperbolic because the travel time of reflected waves is hyperbolic. Something that is important, and this is an important terminology, just consider for a hypothetical data acquisition where x is 0. It means that you place the source and receiver at the same location. In reality, it is impossible to do that, but assume that in a hypothetical data acquisition, you can do that. In such a case, this is the travel time of reflected waves. And you see that the travel time of reflected wave is given by 2h over v1. So 2h over v1 is indeed 0 offset time travel time. It is for the scenario where the source and receiver are on the same location. So 0 offset travel time is t0, and this is given by 2h over v1. In addition to primary reflected waves, we have multiples. Multiples are those waves that are reflected from the source to the surface multiple times. And for example, the first multiple, the equation for the first multiple is given by this equation. And again, T0 is 2h over V1. For the first multiple, something that you should consider here is that at this location where the seismic energy free surface, where you have air has very low density and velocity, so the acoustic impedance of the air can be assumed to be 0. So here is Z1, here, that is Z2. So in such a scenario, the reflection coefficient is -1, and -1 is that the polarity is reversed. I explained how to discern reflected waves from multiples. Assume that this is a seismic shot record and this is a primary reflection. We may get some initial estimate or rough estimate of T0 by looking at the closest geophone to the receiver and consider that travel time to be, close to T0. Now, what you need to do, just consider the time to T0 from this point, like somewhere like here, and look for another reflection event. If you see another reflection event exactly at this time, 2T0, then look at its polarity. If the polarity is reversed with respect to the first reflection event, then you can say that, okay, this should be multiple. It is the first multiple. So the second multiple will appear at, so here assume that the initial polarity was positive. So here the initial polarity becomes negative, and for the second multiple, you're going to see it at 3, T0. And again, the polarity will reverse, so the polarity becomes positive. So this is how you're able to identify multiples from primary reflections. The first thing that you should identify is to identify primary reflection, and then follow this procedure in order to identify subsequent multiples. Is not that big deal for land seismic data, and mostly they are very strong in marine seismic data, and several methods have been developed in order to remove them just to preserve primary reflection. Seismic ghosts are reflected waves that have a different route from primaries. So for example, if you bury the source here, this is your primary wave and this is your ghost. So the travel time of ghost is a little bit longer than primary reflections. And how we see them, if you look at any reflection event closely, you may notice that after the primary reflection, we have several reverberations. So in other words, assume that this is the pulse that is produced by source, and when we look at the data, and once we identify a reflection event, instead of having one or two oscillations, we may see several oscillations. And the oscillation that comes after the first oscillation can be related to ghosts. As I mentioned, we may notice some strong linear events that have some also dispersive nature, and they cover somehow a triangle area on our seismic shot record. And these are ground rolls. So at the same time that the source produces P wave, ground rolls also generated, and indeed ground rolls has very high amplitudes, and sometimes about 70% of seismic energy is converted to ground roll. And The ground role overlap with reflection events. So this is a record with ground role, and this is the record in which the ground role has been filtered. And you see that we can easily follow up a reflection event, but here because of the overlap, we see some discontinuations. Now you may ask me a question how we can identify ground role. In order to do that, just let me ask you this question. Look at a ground role data that you have. And I'm going to go back to the previous slide. Look at one complete cycle of the ground role and compare it with, for example, direct waves or refracted waves. Then let me share with me your observation. If we look at the seismic record, for example, this is one complete oscillation of ground roll, and this is one complete oscillation of P wave. Something that you can conclude easily, ground rolls have longer durations, and this is how you're able to identify them easily on seismic shot records. So if you look at, for example, direct waves or refracted waves, calculate one oscillation and just compare it with this triangle, the waves that we see within this triangle area. Those waves that have longer oscillations can be interpreted as ground roll. So a complete cycle of ground roll is much longer than reflected waves or P waves in general, I can say. Now just let me ask you a question. Can you identify different events on this seismic shot record? Go through this lecture. If you're struggling, watch the lecture again, and I'm confident that you're able to identify different events on this seismic shot record now. Now just let me talk about the concept of noise. When we talk about noise, sometimes we may say that, okay, noise is like the ambient noise that usually we record in environment. But the concept of the noise or signal is much broader. Signal is something that we like and we are getting information from. And noise is something that we don't want it. So in reflection seismology, the goal is to obtain some image of subsurface from seismic data. Yes? And what type of seismic data we want to use? Reflected waves. So reflected waves for us is signal. This is something that we want to keep, we want to preserve. On the other hand, direct waves, refracted waves, ground roll, multiples, ghosts, all of these things are something that can indeed degrade our data and we should get rid of. And as a result, all of these things, direct waves, refracted waves, multiple ghosts are considered to be, ground rolls are considered to be noise in reflection seismology. So first, the concept of noise is relative and something that is considered to be signal for a discipline maybe is noise for another discipline. And in reflection seismology, reflected waves are signals. I hope that you have enjoyed this lecture. Thank you very much for your attention.